Okay, so now I think we can go ahead and get started. We're just going to do some practice, kind of get ourselves thinking about topology, see some new problems that we haven't thought about before, and you know, obviously for the in-class final, I'm not going to be asking like super hard problems. But I just want to give you like an idea here of some of the things to be thinking about, kind of review some of the important results that we've learned, especially some of the more recent stuff. But I'm also going to try and go back and do a few questions from earlier just to kind of remind you, because the final will be comprehensive with a little bit of an emphasis on the chapter 7/8 stuff, you know, the Heine-Borel theorem, the compactness, the definition, all that kind of good stuff. So, and there's a list of theorems for you guys to start learning. So once you sit down and get down to business with this, then you would definitely want to include that in your studying as well. I have not written the final, but it will probably be, I don't know, probably approximately 1/3 of it would be just those proofs. So you know, that's going to be a lot of the points, and then the rest of it's going to be some of these other kind of problems, kind of like what we're going to talk about right now. So I'm going to start with a multi-part problem, which is just going to be to ask you whether the following spaces are compact or not. Okay, so this is a natural question for a class like this. So decide if X is compact. Okay, so the first one is going to be, X is going to be the set of points A comma B in the R squared, such that X is in Q intersected with the interval 1, 2, and 0 is less than or equal to Y is less than or equal to 1/X. We'll start with this one.
X comma Y, right? The order?
Oh, yeah. That should be X comma Y. Sorry. So this is just little x comma little y. Thank you. Okay, so it's just a subset of the R squared. Now I didn't give you a topology here, so you should just assume that the topology is induced from the Pythagorean topology on R squared, right? So that's what we're looking at. Okay, so any ideas what we should do? Maybe what would you maybe do first? Yeah, I would probably draw a picture of it. That's probably a good idea. Let's see if we can draw a picture of this, okay? So you can clearly see that X and Y are both positive. So in my picture, I'm only going to draw the first quadrant of my XY plane. And so we're really interested in X values between 1 and 2. We can see that right here. And let's see, when X is equal to 1, Y is going to range between 0 and 1. So let me put the Y value here. So the point 1, 1, for example, is part of the graph. And when X is equal to 2, then Y is equal to 1/2. And essentially, we're looking at this curve. You know, you can basically set Y equal to 1/X, and you're going to get like this portion of that graph. And you're looking at the whole graph between here and here, but only for x's that are rational. So for any x in here that's rational, so like for example 1.5, y can be anything. So we basically are going to get like essentially a bunch of vertical strips, but then there's also a bunch of vertical. So if we took something like the square root of 2, which is irrational, that whole vertical strip would be excluded, right? And if that was excluded, then the corresponding y value would be excluded as well. Okay, so at any given x value between 1 and 2, we either have a whole vertical segment or we have nothing. Does that make sense? Depending on whether x is rational or not. Okay, so kind of an interesting graph. It's got these, you know, sort of vertical strips that are right next to other strips that are excluded.
Asymptotes?
we're not really talking about asymptotes here. This is, I mean, the asymptotes for the graph would be way over here on the y-axis and the x-axis. It's not really asymptotes, just dotted lines to exclude those points. So does the picture help you to think about this?
Yeah.
What do you think, Vin?
It's closed and bounded.
So it's
Oh, okay, so we're going to try and use the Heine-Borel theorem. So because we're in R squared with the usual topology. Now see, if I had said use the discrete topology, for example, then this would definitely not be compact because it's an infinite set. Okay, so you remember that with the discrete topology, a space is compact if and only if it is finite. Correct. So in this case, this would be an infinite set, so it would not be compact using that topology. But if we use the topology induced from the standard topology on Rn, then you can use the Heine-Borel theorem. So the question is X closed and is it bounded? Okay, so bounded, let's start with that. So X is bounded. Bounded just means the whole entire space can be put inside of a neighborhood of some radius. And the space is right here within this little piece. So you can easily do this because you can basically say that X is contained inside of a neighborhood. Usually I use a little script 0 for the origin with a bar on it. It's the same as the book's notation. And you can just make sure you pick a big enough radius to cover this. You don't have to get it exactly right. You can pick a radius of 5,000 if you want. It's okay. Okay. I mean, you can try to figure out what's the maximum distance away from the origin, but you don't need to work that hard. It's not necessary to come up with the smallest, ball that we can put this space inside of. And in fact, if we use the Pythagorean metric, then the neighborhoods really are just disks. So you can just come out here and make a disk of radius, let's just say we make a disk of radius 3. Okay, so something like that. But remember that when I talked about Rn, I also talked about the other metric where you take, the distance between 2 points is the max of the absolute values of the differences of the coordinates. So if you use that, then instead of getting a circle like this, you'd actually get a square. And in that case, you could find that the radius that you were using isn't going to work for the other shape. But if I pick something that's like a radius of 3, then I don't have to worry about it. So if there's any confusion about which topology to use, you can either ask me or I'll try to be clear. Like here, I probably should just say using the Pythagorean metric. In this case, it won't matter. Like if it's bounded using one metric, it's going to be bounded using the other one as well because because they are basically equivalent. But the actual choice of P might matter depending on how your distance is being defined. So, but in this case, this radius will work for whatever interpretation you might have. Okay, so it's bounded. Okay, now is X closed?
yes,
How come?
because the closure of X is equal to X.
So if the closure of X is equal to X, then that's
But
one way of...
actually, I feel like when we get the intersection here, if you intersect
So
that set,
we're taking just the rationals in here.
so the closure of that is going to be the whole closed set.
So is it
between
the
1
same
and
as
2.
is it the same as X?
So it's going to be different.
So you're
Because
saying
when
the
we do
closure gets bigger.
intersection- Yes.
If the closure gets bigger, then the set
it's
is not
not
closed.
closed.
So you're changing your mind?
Yes. That's what I'm thinking.
Okay. What do you think, Ben?
So
you think it's close?
the closer us gonna to be 1. The closed interval 1, 2. Yeah, it's bigger, so it's not equal the whole set.
Okay.
So
Does everybody agree with this?
So it's
The
not
answer
closed.
here is no.
No.
It's not closed. And the best way to explain it you could say the closure of the set is not equal to the set, but that's almost just, that's answering the question with a question, because now you're asking me to convince myself that the closure of the set is not equal to the set. I would suggest that you just pick a point that's outside of the set. So I would pick something like the square root of 2 comma 1/2, right? So if I take the square root of 2 comma 1/2, this is not in x, it's not in the space, but every neighborhood around this point in R2 would contain points of x. So in other words, the complement is not open. Okay, so this means that the square root of 2 comma 1/2 is in R2 minus x. So it's in the whole plane but not x. However, if I take a neighborhood around radical 2 1/2 of radius p, right, it's always going to intersect x. It is a non-empty intersection with x for all p greater than 0. So for whatever radius you try to draw, right, you're going to end up with a neighborhood that's outside of, a neighborhood that is not contained within here, right? So r squared minus x is not open, so x is not closed. And if x is not closed, then what is our conclusion about whether this is compact?
It's not
It's
compact.
not.
It's not compact, right? So thus, x is not compact. That's by the Heine-Borel theorem. For a subspace of R2, it's going using the Pythagorean metric, the space will be compact if and only if it is closed and bounded. Okay. Now, yeah, so just remember, that R squared is Hausdorff, right? So if you have a compact subset of a Hausdorff space, it has to be closed. So if x was compact, then it would have been closed. So you can also just cite that result. It's not closed, therefore it's not compact.
So it's actually the contrapositive of that
Of that.
theorem, right?
That's correct.
Okay, so I just want to ask, so it's not enough reason to say that the closure of the set is not equal to the set, so we can't say that it's not
Right,
closed?
so the closure x equals x if and only if x is
X
closed.
is closed.
So this is definitely a true fact. This has been true for a long time, way back to the beginning of the semester, or early in the semester when we talked about it. So if your reason for why x is not closed is to say that the closure of x does not equal x, what I'm saying is you're kind of begging the question. You're sort of rephrasing, you're justifying this on the basis of something else that requires an equal level of justification. So you're just rephrasing it. It's
So I think I use the contrapositive of it.
and I'm using the contrapositive of this, yes. But my point is this: if you give this, okay, so you can do it this way too. I don't care.
Mhm.
My point is that's not my point. My point is that using this as your justification for why something is or isn't closed, to me is sort of like you're just rephrasing the question with another equally hard question, or equally clear or unclear justification.
Okay. I just want to make sure.
Yeah.
Because
So if for example, let's say that I have a theorem, and my theorem is that I am happy if and only if it is Saturday, right? Definitely. I'm happy if and only if it is Saturday. So would a good proof of that be to prove that I'm sad if and only if it is not Saturday? Well, that's content-wise, that's equivalent, right? It's going to be basically just as easy, just as hard to prove either one. So I would just argue, like you would be telling me something that's true, but it wouldn't be really leading me to a reason that I want to hear why x is not closed.
Okay.
Yeah. Okay. That's a really good point. That's a really good point. Okay, let's do another one. I mean, usually I try to come up with questions where those sorts of justifications don't really make sense to use. you know, I don't want you guys to spend the exam trying to guess what do you think I'm looking for or what am I really asking. So just come up. You can come up during the exam and ask me. You know, do I have to prove this, 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 or can I just say it's such and such? I'll let you know. Okay. Okay. Let's do another one. Let's do part B here. So part B is going to be the space n cross n cross n, where the first n has trivial topology. The second n has the discrete topology. And the third n has the cofinite topology. That's the one where capital F is closed if and only if f is equal to n or f is finite. Okay, so 3 different topologies on the natural numbers for these 3 different sets. Okay, so can anybody tell me what theorem they want to use for this? Take it out.
Yes.
Whenever you see a question about compactness with Cartesian products, you probably want to use that Tikhonov theorem. So Tikhonov's theorem says that this space will be compact if and only if each individual one is compact. Okay, so is each individual one compact here?
No.
So we have a no.
So n
Because
is
of
finite
the-
or not finite?
Because the discrete topology is
Well, the
not-
n is the natural numbers.
Natural number is finite or infinite?
Which one is it?
The capital.
Yeah, capital N. Is it
N.
finite or is it infinite?
I don't know.
Yeah, you do.
It
Got
is
natural
infinite.
numbers? What's the natural
It-
numbers? 1, 2, 3, 4.
Infinite.
Oh, right now I got
So-
it. I got it.
So using the
Okay.
discrete topology,
Right.
this is finite if and only if it's compact if and only if it's finite.
Right.
So since the natural is infinite, then it's
So the middle N
the middle one is not.
is not
compact.
compact, even though the other 2 are. Because remember, if you use
Yes, the
the
discrete topology.
trivial
trivial.
topology, everything is compact. And then we also show that this one
is compact.
is also compact. So the middle N is not compact. So by Tikhonov's theorem, this space is not compact. So this would be a very natural question for me to ask on the final. It's not too hard, but it uses a very important theorem. It's something we just talked about in the last couple weeks. Okay?
We have that only a finite set with a discrete topology can be compact.
Right, right. That's the theorem. So this is because, yeah, if you want a justification here, you can just say because of the discrete topology. So for the discrete topology, X is compact if and only if X is finite. Okay? Because with the discrete topology, I can give you an open cover which just consists of singletons, right? So you cover your space with singletons. If it's an infinite set, then that's your infinite open cover, and there would be no finite subcover because you can't take any one of those sets away. Yeah, exactly. Okay, so that's a nice one. Okay, let's do another one. So we've done 2 parts. Let's do the third one. Okay, let's do let's do capital X. This should be capital X here, sorry. That's what we're talking about. Okay, so capital X equals, we're going to do half of the real line this time. Interval from 0 to infinity, including 0, where tau has a basis. So I'm going to give you the topology by telling you the basis instead. Has a basis consisting of all intervals of the form closed interval a to infinity, where a is greater than or equal to 0. So this is a basis of the topology. Do you guys remember, in order for something to be a basis for a topology, it has to do two things. Now, the basis, just to kind of review this from chapter 3, the basis itself does not have to be closed under arbitrary unions, because the definition of the topology that you create is that you take all arbitrary unions of your basis sets. So when you're thinking about the axioms of a topology, right, you remember the empty set has to be in the topology, the whole space has to be in the topology, finite intersections have to be preserved within the topology, and arbitrary unions have to be preserved in the topology. That's the definition that we learned back in chapter 3. I definitely think knowing the definition of a topology for the final exam in a class whose title is topology would be a very good idea. Okay, so that's the definition. Now, in order for something to be a basis, well, basically you don't have to have the closure under unions. You just have to have that the intersection of any two of these is another one of these, and that the whole space can be achieved somehow as a union of these sets. Okay, so is the whole space, here's my whole space, can I get that as a union of basis members?
Yes.
For sure. In fact, you can choose a equal to 0 and you get the whole space is in there. Okay, so actually you have the whole capital X in the topology. And if I intersect any two of these, then if you take this one and you intersect it with another one, will it be another interval of this form?
Yes.
Basically, you're just going to compare A and B. You can just say without loss of generality, suppose that A is less than or equal to B. So then the intersection would just be the smaller one, which would be this one over here, right? So then, which is again in the set. So yes, so this does form a basis for a topology. And the topology tau, therefore, is all unions of these types of intervals. Now, of course, because these intervals are nested, meaning that you can actually arrange them with, if I give you any two of them, they're all comparable to one another, right? Just based on whatever this number is. So when you take unions of these things, right, you're actually going to get another one of these things again, right? So in that sense, it was already clear that it's closed under arbitrary unions too. Okay, but that's the topology. Okay, so based on that, so you think this is compact? Yeah. Okay, you think it is. How are you going to convince me? Now, can I use the reasoning that anything about closed and bounded, the Heine-Borel theorem here?
No.
No, because this is not coming from the absolute value metric, right? This is a different topology. So if I'm not using the standard topology on Rn, which in this case is R, I can't use the Heine-Borel theorem for this. I have to think about something else.
The cover, right? You're thinking of cover, and the cover have a finite cover.
So that's the definition of compactness. Is that what you were going to say?
No, I was just gonna make sure that when we're dealing with R and
Yes.
the absolute value metric,
Uh-huh.
even just with the real number only,
Mm-hmm.
we were allowed to use the other theorem that you mentioned.
The
Was it?
Heine-Borel theorem?
Yes.
Yeah, because the absolute value metric, right, the absolute value metric is the, if you go back to the distance metric on Rn, where you're taking the max of these guys, this is the one that you use the Heine-Borel theorem for, right? But if there's only one value of I, if it's only just R to the first power, then you can just take off max and you just
I
take
just
literally
do
that.
absolute value.
It just reduces to that, basically.
Okay.
Yeah, exactly.
I just want to confirm.
Yep, absolutely. So we could use the Heine-Borel theorem in that case. Okay, questions, comments before we do anything here? Oh, I was thinking about using an open column that says X is compact. If any open cover consisting of basis elements has a finite subcover. Okay, basically what Vin was saying, get kind of back to the definition more or less, to prove that it's compact. Is that your point as well, or?
I was actually going to solve it, but yeah.
Okay, so it sounds like we're all pretty much getting there. So the idea is to take an open cover and show that it has a finite subcover. So let's let the set, now guys, when you're proving this, that something is compact, you have to make it an arbitrary open cover. So that U sub I be an open cover of the interval from 0 to infinity, right, which is our space X. So our job is to come up with a finite subcover. Okay, so this just means that the interval 0 to infinity is just the union of the U sub i's. And Alex, you're right. We could just stick with a cover using basis elements, but we can also just do it this way. We can just take any open cover. It's not going to really make a difference. Okay. Any thoughts on what I can do with that? Do you know what to do?
Yeah, I was going to, without loss of generality, arrange them by the well-ordering axiom. You have a bunch of nested things, and
Okay.
You would have a least element, which would contain all the other sets.
So that'd be kind of like a greatest element, I guess. Oh, you mean a least element in R?
Yeah.
Yeah. I mean, that's exactly right. Let me just point out the easiest thing to say here, guys, is that 0 has to be in one of these, right?
Mm-hmm.
Well, if 0 is in one of them, what is that? All of these U sub i's look like unions of these, right? Well, so then one of these intervals has to be the whole interval 0 to infinity already. And so you can just reduce this arbitrary open cover to a cover that has just one set in it, which is this set itself, right? So here's the clever thing about it. Any open cover of this space must have the whole X as one of its sets, right? So my point is, note that for some I, U sub I has to actually be the whole space 0 to infinity, right? Thus, let's call it U sub I naught, just to fix it. So then the set which just has only U sub I naught in it alone is a finite subcover. I've seen people kind of getting a little bit mixed up about compactness in the proofs that I've seen. I've seen people do this to prove that X is compact. I've seen people do this. X is compact. Instead of starting with an arbitrary open cover and producing a finite subcover, I've seen people prove that this is compact by just writing down a finite subcover. Guys, of course, this is a finite subcover of X. It covers X. It's got only one set in it, right? But this is not how compactness is proved. What you're doing here is you're showing me that it is possible to cover X with a finite number of sets. But that's always true. If this argument was valid, every space would be compact, because this is always has to be in your topology. So you could always just use this one open set and cover the whole space. But no, what you have to do for compactness is take some arbitrary open cover that maybe doesn't have the whole space in it, right? Now in this case, we actually proved that the whole space does have to be one of the sets that's in that open cover. Because whichever set 0 belongs to, right, whatever set 0 belongs to, well then that set has to actually be the whole space, because the only open set in tau that has 0 in it is actually the whole space. Right. Okay, that's kind of like that problem on compactification. Do you remember the one where we sort of threw in a new symbol called infinity, right? And then we made a topology on this, where we said, well, the topology is going to be everything that's open in R using the absolute value topology together with this whole space, right?